Hello everyone, and welcome to this presentation on maximum power point tracking of photovoltaic systems using Extremum seeking control. Now this particular application is looking at how we can derive the maximum power that is generated by a photovoltaic system using a relatively novel technique, and this is where the interest of this particular presentation lies. So the first thing that we're going to look at is the non-linearity that exists in photovoltaic systems. In particular, we're going to look at how the power that is generated depends on the solar radiation as well as the temperature. And then we're going to look at the application, that is the maximum power point tracking, and how we can do that in this particular case. Also, we're going to look at how a DC-DC converter in between the photovoltaic system and a battery, for example, or any particular load that you may have allows us to do this conversion in a very smooth way. And then we're going to look at the technicalities of extremum seeking control and this particular technique, how we ensure that with this particular approach we are operating at the maximum power point. And finally we'll present some results. Okay, so here is the block diagram. So on the left hand side you can see the photovoltaic system, and the voltage around it, that is generated by the photovoltaic system, is given by V subscript PV, and this voltage is then fed to goes to a dynamical optimizer, which is driven by this microcontroller here, and the microcontroller itself takes two measurements. First, you have a voltage sensor which takes a voltage, that is in this case VPV, and the second measurement it takes is the current that flows through the photovoltaic system, that is towards the dynamical optimizer. So these two measurements are taken by the microcontroller, and it processes that measurement and does some manipulation with it, which is where the whole algorithm comes in, and then generate a driving signal which is used to ensure that we are always operating at the maximum power point. And at the output of this dynamical optimizer we have a given voltage, which is we know, which is what we want to keep more or less as a constant value. And then you have the load, which could be in this case a battery or a resistor or an inductor or a combination of these. Okay, so this is an equivalent circuit model of a PV panel, right? So as you can see on the left hand side here we have the sun, which is a source of all the energy that we get from the photovoltaic panel, right? If there's no sun, then there won't be any electricity that is generated from the photovoltaic panel, and there won't be any power that we would receive. So the sun is directly responsible for generating this current IPH, which is the current that is generated by the photovoltaic system, and then you have the diode D, parallel resistance RP, and the series resistance RS. And at the output of RS we have the current I as well as the voltage V, which is what we see on the terminals of the photovoltaic system. Now the first equation that you see is responsible for generating IPH, and IPH is, as you can see, proportional to S, where S is the irradiance level of the sun, right? So that's measured in like watt per meter squared, and also you can see that it is dependent on T, and T is the temperature, right? I won't go into too much detail about these or each of these particular terms. The second equation relates I, that is a current that is seen at the output of the photovoltaic terminal, to IPH. Then we can also see there is some exponential relationship between I and IPH, and again we have a dependence on temperature in this particular equation, right? These two equations are the most important equations towards the behavior of the photovoltaic system, and I'm not going to go into too much detail about explaining each of these, but what we're going to do, however, is to actually plot the voltage and the current as well as the power and of the photovoltaic panel for different conditions, and look at how each of these parameters affect the power that we obtain from a photovoltaic cell. That would be much more relevant and easy to follow. So here is the typical current versus voltage characteristic of a photovoltaic panel. So as you can see here on the left hand side, we have the current, short circuit current ISC, and when the voltage is more or less zero, that is the photovoltaic panel voltage is zero, you have a current, a large current of around 8. That's for one particular typical photovoltaic panel. And as we increase the voltage, we find that the current actually drops gradually, and at the far end we have the other situation where you have the open circuit voltage, that is a large voltage, the magnitude of around 33 volts, and the current there is very small. And in between these two extremes, we have what we call the maximum power point. The maximum power point is basically the point where the product of the current and the voltage is a maximum. Now, this particular current versus voltage characteristic happens at one particular condition of radiation or irradiance for a particular value of S, as well as a particular value of temperature. So if we change either S or T, this curve would change in different ways, as we'll see very soon. So basically what we want is for our system to operate at the maximum power point, where you can see there's a drop in the voltage, so the voltage is not its maximum value, and the current is also not its maximum value, but the product of these two result in maximum power generated. Right, so here is where we're looking at the power versus the voltage characteristic of the same photovoltaic panel. So in this case, what you find is we're looking at it for different level of irradiation. So, right, so we're looking at three cases in particular: 500 watt per meter square, 750, and 1000. Right, so these are the different irradiance levels that a photovoltaic panel can experience. And as you can see clearly, so for a small level of irradiance, so at 500 watt per meter square, our power is around 100 watts, and for 1000 it's around 200 watts from the photovoltaic panel. Now, what is also interesting here to note is that the maximum power in this particular case, as we change the irradiance level, occurs at the same value of voltage. Here in this particular figure, what we find is with varying the temperature, right, for different temperature levels, we are looking at how the power varies again with voltage. So in this case, as the temperature increases from 298 to 328 Kelvin, we find that the maximum power point has dropped, right, from around 170 to 140 watts. Note also here that the voltage at which the maximum power point has also moved, right? So for 298 it was around 28 volts, but for 328 Kelvin it's around 23 volts, right? So the voltage at which you have the maximum power changes. So in practice we have to deal with a situation where the temperature of the panel is changing as well as the irradiance. In fact, the two of them are kind of connected. So the maximum point is always moving around. It's not something that is static, and we always have to be able to track this particular maximum power point. Here is a graph of a normalized current versus voltage plot. So in this case what we are doing is we're connecting, for example, a resistive load to our photovoltaic panel, directly connecting it, and as a result of this we find that the operating point will be determined by the straight dotted line. So as for example for a particular value of let's say 0.2 volts, then the current would be 0.25 ampere, of course, normalized values, and it follows a straight line because of Ohm's law. Now, depending on the level of irradiation that we have, the point at which we operate will also depend on the particular characteristic curves. So in this particular case, as we change the level of irradiation, we operate at different points, and the maximum power point are represented by the square blocks. As you can see, is moving around as well, and as it is moving around, it is not necessary that we're operating at the maximum power point for that particular load. So that is clearly a problem where we want to achieve or obtain maximum power from the photovoltaic panel. So this is the scheme that we use for maximum power point tracking, and in this particular case we have a battery that is connected to the output of the photovoltaic cell, and this battery is at a voltage of around 24 volts in this case, and the voltage and the current from the photovoltaic side are given by VSA and ISA, and these two are fed to this maximum power point tracking control, which generates the duty cycle that is then fed to the switch mode power converter, and at the output of the switch mode power converter we have a voltage which is given by V converter out and a current I converter out, and this is what supplies the battery. In this particular case, what is of interest to us is this maximum power point tracking control, which determines the duty cycle to maintain the voltage that is necessary at the power output, as well as the current that is necessary to drive to keep charging the battery. Right, so going in a bit more detail now to show you exactly what's involved in this particular application. So we have the photovoltaic panel which generates a current, and then we have a series of capacitors and inductors. I won't go into the detail of why they need to be there, but they're generally there to smooth the voltage and the current that goes through the load. And then what is of interest is this particular switch where we feed the signal D, right? And this signal, which is the duty cycle, basically determines when the power switch goes on and off, and as a result of this we maintain a given voltage at the output as well as a certain current which is then supplied to the DC bus, which could be any load or a battery or anything. In terms of the extremum seeking control, what we're doing is actually we're seeking the maximum power point. In this case, if you look at the graph between y and x, we want to track the maximum power point, that is the peak of this particular graph. And the way we do that is by differentiating the particular output y, and based on that we obtain a measurement g, which is then fed to a kind of a logic circuit. Right, this is not necessarily a binary logic circuit, but for simplicity here we're putting it as a logic circuit, which generates an output epsilon, which is multiplied or scaled by a factor of k before being fed to an integrator, which then determines the direction in which x will move, such that we track that maximum power point. So the key element here, if I were to choose one, would be the differentiator, which actually gives a measure of the gradient, that is, of how y is changing with respect to x. That is, as x is changing, how is y changing, and that information is fed back to the logic circuit, which then determines the direction in which x should move to track the maximum power point. On the normalized power versus voltage graph, this is what it would look like. So if you were operating at the point x1, let's say at the beginning, then as we change the voltage, then the power would be increasing, and if it is increasing, then it means that the gradient would be positive, so it keeps moving in that same direction to x3, x, and so on until it reaches the maximum power point x of k. And if, on the other hand, we were operating on the other side of the curve, then as we keep increasing voltage, let's say, then it would be clear that the power would be decreasing, so the gradient would be negative, which then means that you have to move in the opposite direction to seek the maximum power point. Right, so just to give you an indication of how this whole circuit operates, we have here a series of waveform simulation results. And so in this case, initially, we are starting the photovoltaic system as an open circuit, and this is represented here by VSA, which is at quite a large value, and the current ISA, as you can see, is very small at the beginning, as well as the power PSA, which is also very small. Now these are the three parameters which are of interest to us, and as we connect the load to it, as well as the power DC to DC converter, and we start up the system, then immediately what we find is VSA drops to a smaller value. In this case, of course, I have to remind you that we're connecting a battery to it, which means that the voltage at the output is higher than the voltage at the input, so therefore the DC-DC converter is working as a boost converter. So the VSA actually drops to a smaller value, and ISA increases such that the power that is the product of V and I becomes a maximum value, as can be seen here. So the power rises very quickly and achieves and reaches a maximum value in a very small amount of time. And the voltage VC here, what we're showing, is actually the voltage that is responsible for determining the duty cycle of the switch that we saw on the previous slide. Okay, so that's it for this presentation. I would like to thank you for your attention, and would welcome any sort of question that you may have. Thank you very much.